Welcome everybody to the second session here. We're going to go over the gas laws. We're going to look at the properties of gases, how we measure them using their four measurements: temperature, volume, pressure, and amount, which is measured in moles. And we're going to talk about their physical relationships and how those are described in easy equations called the gas laws. So we have our simulation up here from FET, Colorado, University of Colorado puts these cool simulations up. I know it's not streaming at the highest frame rate for you because I have the meeting up on another computer, but we can still use it to kind of understand because we're going to be looking at the numbers on the temperature scale, on that pressure scale, and then looking at the volume of the chamber, this chamber here, and we're going to look at how it affects, how each change in pressure, temperature, volume affects the other measurements. So today, a good thing to have up is, oh, I didn't open the right one, is the practice problem PDF. We're going to add to it. You don't need your cameras on, but if you want to see, if you want it to be a little bit more formal, you can see me over in the corner. But either way, I don't know if you need to see that picture of me talking. I'm a nerd, have a big old gaming headset on so that it has better audio. So yeah, fun stuff. But again, you don't need to turn your camera on or any of that stuff. And I don't really need to have my camera on either because we're looking at the screen today. I'm not that entertaining. I'm just a goofy old man. So anyway, let's turn this off. So yeah, you can just turn your cameras off unless you want to, show us something cool. And again, just talk in chat and say, Mr. Sullivan, I'd like to show you something, and then I'll turn your camera on or what have you. All right. So a good thing to have open today is the practice problem PDF, because, or if you have the ability to print, page 17 is going to be a very helpful page because it's going to be a nice little cheat sheet that we can make on what the actual law is, what things don't change in the law, and then you can make your notes on this piece of paper here. And then, of course, I'm going to show a couple examples from the other page that I assigned this week, which was page 6. So we'll have that up, ready to go. All right, so let's take a look at the book real quick. For those of you following along in the book, this stuff corresponds to chapter 14. Section 1 goes over the first 3 laws we're going to talk about, which is Boyle's law, Charles' law, and then Gay-Lussac's law. We have kinetic theory, which we talked about last time, which is the idea that gases are tiny little balls that bounce around and hit each other and don't interact. They have weak intermolecular forces, is a fancy way to say it. And so therefore they're buzzing around and they're taking up space and they're exerting pressure on their containers. And so therefore they have a pressure and they have a volume. And the temperature of a gas is going to be the average of all the movement energy that they have. So our temperatures are energy measurement. And then finally, the amount of gas is measured in moles. Now, in this case, our little simulation here represents amount as just the amount of stuff that's in there. I can obviously pump some more in there, and you'll see the little balls slowly, poorly fill in the chamber. So if you are following along in the book, chapter 14, section 1, and a little bit of section 2, because we're going to talk about what's called the combined gas law as well. I'm going to reference this just to show pictures out of it, because again, it's a reference that you should all have. I have the PDF version of it. You guys probably have your physical version, or maybe you have found this online. I found this very easily online. So yeah, let's get into it. So a long time ago, during the age of uh, Enlightenment, during the whole scientific revolution, we all talked about how Newton did his, principles of physics and came out with this laws that govern Newtonian mechanics and all that kind of stuff. But that was more like what we call theory based a lot of the times, because he was just kind of showing the math. When it came to the actual like hands-on laboratory, like what's called practical application, one of the best scientists was Boyle. Boyle is pretty much the father of the scientific method. He's at the time he would have been just as popular as a figure as Newton was. Um, and one of the things that Boyle was uniquely interested in was the relationship between pressure and volume. They had some better tools at this point. They had better glassware. They could make better connections. They had better scales. And so what was one of the things that Boyle was inspecting was what happens when the temperature is held constant, but you change the volume or you change the pressure, what happens to a gas? So you guys inherently understand this. So if you took a balloon and you squeezed it, would you think the pressure went up or down inside the balloon? Well, when you squeeze a balloon, the balloon resists you squeezing it, so the pressure in the balloon must be going up. So how much is this pressure changing though? How much is this volume changing though? And that's what Boyle wanted to know. Boyle wanted to know is if you were to, as you can see down here, Boyle's law, if you were to have a chamber and you were going to change the volume of the chamber, how much does the pressure increase? Or if you were going to like increase the pressure in that chamber, what will it do to the volume of that container if that little like plunger you see there is able to move around? So he did a bunch of experiments, and this is why he's kind of the father of the scientific method. Is it was like, okay, come up with a hypothesis, only test one thing, let your results stand for themselves. And so what were some of his results? So what we have done here in our simulation is we have made the temperature hold constant so that we have constant temperature. So if we look at Boyle's law on that page 17, it asks what is being held constant, and the answer is temperature is being held constant. So let me do, they'll let me write on it. Okay, so in this case, we have temperature is being held constant. And the other thing that we have in our simulation that's being held constant is we have a lid on it. So we're not letting the gas in and out. So the other thing that we are holding constant is amount of gas. So this is usually in what's called Kelvin or degrees C. And in this case, we have amount. Can't spell it there. What am I writing? It's blocked my screen. It shows everything. Oh my god. Oh, because it took a screenshot of my screen. All right. Unfortunately, nope. Every time I try to go get the stuff, it brings up the other. So we'll move that out of the way. There we go. Okay, you guys aren't seeing that little green bar you're seeing right there is what I'm talking about. There we go. Okay. So amount of gas. And the amount of gas is usually N, and it's in moles. So sometimes they call it N. Sometimes they'll just say moles. Sometimes they'll just say amount. So, so anyway, that's what's being held constant. So what's changing is we're going to be changing the pressure, which is measured P, and we're going to be changing our volume. So the question is, what is happening when we change the pressure and the volume? So let's take a look at our simulation and see what happens when we change the pressure and we change the volume. So we don't need this. So let's get rid of this. Goodbye. Okay, it was a bar showing me who was talking. Had to get it out of my way. So as you can see, we have a fixed volume in our shape here. And this handle we can use to move the volume around. So what we're going to do is we're going to make it as small as we can, and we're going to hit reload. So that what we can do is we can see.
You guys are in the house all day, right?
So we can see the pressure as we add some stuff in here. And we're going to increase the volume of our container. We're going to double the volume of our container. We're going to see what it does to our pressure. So what we're going to do is we're going to make this a nice even number. Oh, that was almost pretty good. Let's go to like 50. Okay, it's pretty close. So we have 50 atmospheres of pressure in here. You guys remember the pressure measurements from last time. We have 50 atmospheres. So that would be 50 times 14.7 to do the PSI. So it's very pressurized inside of here. But that's good because we're going to be using this to show, so you can actually see the numbers change in a understandable way. So what we're going to do is, this is would be an experiment that Boyle would have done. We're going to take this and you can kind of see we're going to double the volume. So it's going to be about that big. And what do you notice happens to the pressure? We doubled the volume. We multiplied the volume by 2. And what happened to the pressure? The pressure appears to have been cut in half. So the pressure went down by 2 and the volume went up by 2, by a factor of 2. And that's what Boyle did. He did this experiment over and over and over again to see if that was a consistent finding that he had. Now, we can't do another doubling, but what we can do is we can add another, like a tripling, and you'll notice that we get close to the 12.5. It's not exactly equal to another third, and that's why it doesn't equal exactly out to the 12.5. But either way, you can see the relationship there that is taking place. The pressure and the volume are in what's called, so here's Boyle's law. Excuse me. This participant window is in the way. So we are talking about what's called Boyle's law. And what he noticed was that they are what's called an inverse relationship. If you increase the pressure, the volume will go down, and vice versa. If you decrease the pressure, the volume will go up. This is what's called an inverse relationship. Basically, inversely proportional, meaning if one is multiplied by 2, the other one will be divided by 2. If you look at your book, you can see the graph here shows that. At 1 atmosphere, we have 10 liters. At 2 atmospheres, we have 5 liters. Because what we did there is we doubled the pressure, so we're going to half the volume. And then if we go and not double it, because that would be 4, if we just go from 2 to 3, if we look at our original value, that was a third. And so we have the, let's see, okay, they are saying the 4 atmospheres. They're just not actually talking about this 3 button here. when you read this graph. So anyway, if you look at the fourth, that's another halving of the volume because we have another doubling of the pressure. And so that is what made Boyle's findings so profound, is that he was able to show that no matter the gas and no matter the situation, if temperature and amount of gas was constant, then the pressure volume would be inversely proportional, or what's called indirectly proportional, meaning one goes up, the other one goes down. So another way to say this instead of inverse is indirect. If either way you understand it is fine. So how do we represent an indirect relationship when it comes to an equation, an equality? And so if we think about it, say for instance we have the data from the book here. We have 1 and 10, 2 and 5, and 4 and 2.5. So the 1 ATM corresponded to the 10 liters, but when we went to 2 ATM, that corresponded to 5 liters. Well, how could we set up an equality where these two things come together to make this statement true? How is 1/10 equal to 5 over half? That doesn't seem to make sense, right? Well, I hit the wrong button. So the way it works is multiplication. If we do 1 times 10, that has to equal to 2 times 5. So for this equality to make sense, what we need to do is we need to have the equation, the pressure and the volume at the beginning have to equal to the pressure and the volume at the end. And so what we're going to do is we're going to multiply them together and set them equal to each other. So Boyle's official law would say that the proportionality is such that the product of the two numbers has to equal a constant. And that's what the book is saying here, that the reason why these two things are being set equal to each other is that the ratio of pressure and volume, when multiplied together, will create a gas constant. Then because the gas constant is always the same, it doesn't matter what pressure you have, you will have a corresponding volume and vice versa. So it's basically summed up in this very easy, just if you want to know the pressure of a system after you change something about that system, you can use this equation if the only thing you're changing is volume. If more things are changing, then we'll need another gas law. But that's what Boyle's law does. So pressure volume equals pressure times volume. And that is Boyle's law. So if we look at our periodic table, okay, our PowerPoint here, we talked about Boyle's law, says the things I already said, and then we have some examples. So let's take a look at some of these examples. We'll do example number 2 here. It says a helium-filled balloon contains 125 milliliters of gas at a pressure of 724 millimeters of mercury. What volume would it occupy at standard pressure? So we're going to go over here. We're going to take, actually this will let me write on it. There we go. We'll go to draw and we'll use red because this is blue. So we have here our volume and we have here a pressure. We have to look at the units to recognize what numbers these are representing. So in this case, this is milliliters. So that's going to represent a volume. And this is mmHg, which we remember from last time is a pressure. So then it says, what volume? So the question is, what volume would it occupy at what's called standard pressure? So this is a good example because now we're going to talk about what is standard pressure. So remember, this is the age of Enlightenment. And one of the big things, the scientific revolution, one of the big things, N stands for the amount of gas, Stacy. So we'll get back there in a second. One of the things that was so important about the scientific revolution was that they were talking to each other. And they were doing reactions inside their different houses, inside their different labs. And thus meant the temperatures were different, the pressures were different, because as we remember from last time, depending on your elevation, your pressure in your room is going to be different. In Glendora and Redlands, where I'm at, the pressure is pretty similar. We're probably pretty close to each other. I think we're both about the same amount off the ground. Then we could do experiments pretty close to each other. But if I'm hanging out with my friend, if I'm corresponding with my friend in Italy and I'm doing my experiments in France or England or Germany, I might be at vastly different elevations. Also, the temperature during the day might be very different. So to try and standardize all of their measurements, they all agreed upon a standard temperature, that they were going to always start their experiments at this same level. So whenever you hear the word STP, or standard temperature and pressure, this is the pressure at sea level, so 1 atm, and then they set it to 0 degrees C as the standard temperature. And there was a very important reason why they picked 0. Is it because everywhere was cold during this time? No. 0 degrees C is very cold. And so because it's very cold, what it does is at 0 degrees C, the water in the air starts to try and condense out. And so there's a lot less water in the air at 0 degrees C. Also, it was pretty easy to bring your experiments or your experimental chambers down to 0 degrees C. You could use some ice, or you could use some other methods that they had to bring the temperature down to 0 degrees C. So it did a good job of getting the water vapor out of the air, and it also kind of made it so that everything was standard across the board. There's a problem with this, though, as you guys will see in our next couple laws, is if we're going to use degrees C in mathematics, that's 0. And anytime you multiply something by 0, you get 0. So we're going to need to change that. So our problem down here asks us for the standard pressure. So this is our pressure 2, and standard pressure is 1 atm. Well, remember from our pressure discussion that 1 atm is equal to 760 mmHg. That's another thing that you can have written on your paper right here. If you go to the PDF, you scroll down here, it has a box for the pressure measurements. You can write in all the pressure equivalents here in this box. And another good reason why to have this all ready to go. So yeah, going back to what we were talking about a second ago. What was I writing on? Okay, right here. So we have our pressure 1, we have our volume 1, we have volume 2 as the answer to this question, and we have pressure 2 as the other piece of information. So this is a Boyle's Law problem because the only things we have are pressure and volume. That's how we're going to identify the different laws when it comes to like page 6. We're going to ask ourselves, what is the information they gave us, and what is it they want to know, and what is the information that is being left out or just isn't important. In this case, they told us nothing about temperature. They've told us nothing about amount. So this is the only law that we can use is Boyle's law. Here's my pro tip. I like to solve for the variable that we are looking for before I plug in numbers. So this is just algebra. These are being multiplied by each other. So what we're going to do is we're going to divide both sides by volume 2. This will cancel volume 2, and we'll be left with pressure. Or no, wait, we want the answer here. My bad. Hold on. Boop. If you could mute yourself, that'd be sweet. How satisfied are you with using the touchscreen? Well, I clicked on the eraser and it didn't erase, so you tell me. All right, so we want volume 2. So we're going to divide both sides by pressure 2, because what that will do is it will get us volume 2 all by itself is equal to mute and mute. All right. Volume 2 will give us pressure 1, volume 1 over pressure 2. So now we can just plug in our numbers, and it's not very difficult now. Where our volume 1 is 125, our pressure 1, 724. So 724 mmHg. Our volume 1 to 125 milliliters. And then our pressure 2, which is standard pressure, is 760 mmHg. Now, what I love about the gas laws is that you can actually think about the logic of the problem. Remember that the logic of Boyle's law is that if the pressure goes up, then the volume goes down. If the pressure goes down, then the volume goes up. In this, we can see that the pressure is going up. So our answer should be going down from our original number. So when we plug this into the calculator, if we don't get a number smaller than 125, then we know we've done something wrong. So let's bring up our calculator. Move it out of the way. Okay, so we have to do 724 times 125. And then we're going to divide that by 760. Hey, and that's smaller than 125. We have 119.1. So this is going to equal 119.1. Yeah, it's not going to let me right there. So 119.1 milliliters. That's smaller than we originally had. Remember the inverse relationship, pressure goes up, volume goes down. The pressure went up. It didn't go up very much. Went up very much, didn't change much at all. And then, so therefore, the volume is going to go down. Not very much at all. Stacy says, where did I get 760? Remember that, let's get rid of this. All the pressures, this is what you should have written down here on this page if you don't have it written down. Is the pressure equivalence from last time. So in this box down here, you should have written 1 ATM is equal to 760 mmHg, which is the same thing as 760 torr, which is the same 300 pascals, which is the same thing as 10. Finally, because this is America, it's the same thing as 14.7 to each other. The reason why we did mmHg instead of 1 ATM in our problem here is because the problem gave us mmHg. So let's do ourselves a favor and not have wrong numbers in there that don't match, because again, it's all about the units canceling. We got to kill this mmHg and get left with milliliters, because that's what this problem wants. It wants volume. All right, well, let's go on to Charles. So we'll restart our program here. And Charles is a hot air balloon enthusiast. He loves hot air balloons. And one of the things that he's super confused on, they're not going to show a picture of a hot air balloon. Okay. Thought it did. Either way, one of the things that he's super confused of when it comes to hot air balloons is, why does a hot air balloon float? Like, what's going on there? Just because we get the balloon air hot, why does it fill up the bag? Show directions to hot air balloon. So why is it that putting a little fire down here in the bottom of the hot air balloon causes it to inflate? And then why does it float in the air? Because it's really just filled with air. That air's just hot. So what is the relationship between volume and temperature? And that's what Charles really wanted to know. Unfortunately for Charles, is he wasn't very good at math. He was really just a financier of things, one of those types of aristocrats. And so what he wanted to do, it's not letting me. Let's reload our simulation here. Laws. Anyway, what Charles wanted to do is he wanted to understand the relationship between the volume and temperature. So let's go back here. I want to hold certain things constant. It's not letting me do that. Let's just see if it'll do it. Okay. So what's going to happen is, what happens to the volume of the gas if we heat the gas up? And unfortunately, this little program isn't going to help us. It's not going to show anything. It's just not, it's supposed to change this chamber. If we heated this gas up, it should have pushed this chamber open like that. But it's not working. And they took away the old simulation, so my bad. Either way, let's take a look at the picture that we have in the textbook here. Basically, if you take anything and you heat it up, it's going to basically cause the little air molecules in there to be able to take up more space because they're moving around. And so therefore, the volume and the temperature come up to what's called a direct relationship. All right. So Charles' law is looking at what is the relationship between volume and temperature. Charles was keeping the pressure constant and the amount of gas constant. N is amount, remember. And both of these are constant. They're not changing. If we look at a hot air balloon, the air inside the balloon is pretty much trapped. It's how it actually controls the balloon's up and down movement. Is there's a little valve at the top of the hot air balloon or at the sides, depending on your balloon style, that lets the air out. So the amount of gas is being held constant inside the balloon, and the pressure is being held constant inside the balloon because the gas from the bottom is able to kind of commingle with the air outside, and so the pressure is the atmosphere's pressure. So because pressure and amount aren't changing, so P and N are constant, we're just interested in the relationship between V and T. So at the time, though, in Charles's world, there's no such thing as Kelvin. So there's a problem. What Charles was doing when he was recording his experiments, he was noticing that if you took our little chamber here with the little plunger here, and we measured the volume inside this chamber, say the volume equals 1 liter. When he went over here and he made the volume, he heated it up with fire, right? We got fire down here. When he heated it up, when volume equals 2, if he started at STP, the temperature equals 0 degrees C. Zero degrees C. When he heated it up, he didn't notice that what is double of 0? Also, when he heated it up, to get to the second volume, he had to get it really, really hot. He had to get it up to 273 degrees C is 0. And to see the double, we had to double that degrees in Kelvin, so to have 546. So he didn't notice a doubling in the volume until he heated up that gas to 273 Kelvin. And he didn't notice that the volume get up to volume equals 3 until we had another additional amount of temperature. So in his system, because he didn't have Kelvin, his math just didn't make sense. There wasn't a very good proportionality to the temperature and pressure. So he had huge amounts of data though. And it turns out that his friendship with Boyle was what really helped, because Boyle was able to look at his data and say, oh, the problem you have is that temperature isn't in degrees C, it's in some other relationship. And the guy that figured it out was Kelvin. Remember that the Kelvin scale is the temperature of degrees C. But instead of 0 degrees C being water freezing, he set his scale to be 0 down here, 0 Kelvin, and this same mark is 273 Kelvin. He just took the exact same scale and he just got rid of all the negative numbers. That was another problem with Charles's data, is that on cold days where the temperature dropped into the negative numbers on degrees C, the math didn't make any sense. You got negative volumes. So when we use temperature in Kelvin, so the pressure and the amount are constant, and when the temperature is in Kelvin, what Charles found was that they are directly related. They go up together and they go down together. You can practice this. You can check this out at home if you want. You can go find a balloon. Any old balloon is fine. Blow it up and put it in the freezer. The balloon will shrink. And the reason for that is the air outside the room is hotter than the air inside your freezer, and so the volume will go down. So if this is called a directly proportional, a direct relationship, and if an indirect relationship was a multiplication equality, a direct relationship then is a division equality. So this makes sense if we think about our data in terms of the Kelvin relationship. We had 1 liter, and we had that at 273 Kelvin because we were at 0 degrees C in our hypothetical example I just drew. Once we got to 2 liters, for this equality to be true, this is times 2. So this had to be times 2. So that's where the 273 Celsius comes in, but in this case, it's 546 Kelvin. If we didn't use Kelvin, this was the problem with using degrees C. 0 degrees C is now equal to 2.0 liters all over 273 degrees C. is this a correct equality? Is 1 over 0 equal to 2 over 273? No. So that was one of the problems. The other problem was, what if this was a cold day and we came out and we did our problem at negative 20 degrees C? Well, you still heated it up. It still went from 1 liter to 2 liters, but it didn't say positive 40 down here, because that would be what the math would suggest, right? Negative 20 times negative 20. That should be negative 40, right? Negative 20 times 2 is negative 40. Well, that didn't work. It didn't get colder. What actually happened in reality is this got up to 256 degrees C. And again, that doesn't look like a good proportion. However, if we use the Kelvin scale, then this is actually 256 Kelvin. Sorry, 53 Kelvin. And then this is 506 Kelvin. That is the direct proportionality. So looking at our PowerPoint here, we have Charles' law. It says direct relationship. We have to use Kelvin. Otherwise, we get negative volumes, which we can't have, but also that the proportionality wasn't true under that law. Let's take a look at an example here. We'll look at the second one here. A balloon filled with oxygen gas occupies a volume of 5.5 liters. If the temperature of the gas is doubled, what is the new volume? So we don't actually need to see it. All we know is, if we look at our problem here, this is V1, and they didn't give us T1 or T2. All they told us, though, was that they want to know V2, but what they told us is that T2 is equal to 2 times T1, because it says the gas is temperature is doubled. So if T2, if our setup here is volume 1 over temperature 1 equals volume 2 over temperature 2, and we want to find volume 2, again, my pro tip was to do the math before. So now we have volume 2 is equal to volume 1, temperature 2 over temperature 1. But remember, we just said that temperature 2 is just 2 times temperature 1. So we can rewrite this as volume 2 is equal to volume 1 times 2 times temperature 1 all over temperature 1. So the temperature 1's cancel. And so volume 2 is just equal to 2 times volume 1. Volume 1 is 5.5 liters. So 2 times 5.5 liters. 5.5 times 2 is 11. So this is volume 2 is equal to 11 liters. So if we wanted to do an example with Kelvin, we could do that too. I know this video is running long, but you can speed it up at 10 times speed if you want, whenever we're doing, if you're watching the video. Or at least, what is it, 2.5 is as high as it goes? It'll be on YouTube after this. All right, so if we look at the, I'm erasing the wrong one. There we go. If we look at the first example here, where we actually have temperatures, then what we're going to want to do is we're going to make sure that those temperatures are converted into Kelvin. Otherwise, the math doesn't work. And this is the number one example I see students make whenever they do these problems, is they forget to convert it into Kelvin. So we have a volume, because it says volume, and it says 36 degrees C. So we also have another volume. So we have a temperature 1, we have a volume 1, and we have a volume 2. it wants to know what is temperature 2. So volume 1 over temperature 1 equals volume 2 over temperature 2. We want temperature 2, so what we're going to do is we're going to solve for that first. Again, this is where your algebra skills come in. The way to get this by itself is we're going to get temperature 2 by itself. If we divide both sides by volume 2, okay, this will give us volume 1, temperature 1, volume 2 is equal to 1 over temperature 2. So to fix this, we got to flip both of them over. There's other ways to do it, obviously. You don't have to do it exactly that way. So what this will give us is temperature 1, volume 2, volume 1 is equal to temperature 2. So now we can start plugging in our numbers, as long as we first remember that we can't have degrees C in our problem. We need to have Kelvin. So Kelvin is going to be equal to degrees C plus 273. So 36. So our Kelvin is going to be 36 plus 273. Add the 6, that gives us a 9. Add a 3, that gives us 300. So our Kelvin is 309 Kelvin. So now we can plug this in. Temperature 1, 309 Kelvin. Volume 2, 789 milliliters. You can put them in brackets if it helps you keep track of it. And then we're going to divide it by volume 1, which is 1496 milliliters. Now again, what's awesome about these problems is that we can use our logic. They're direct relationship, meaning one goes down, the other one goes down. Our volume went down basically by half. So that means our temperature is going to go down by half. And again, the reason why we had to switch to Kelvin is that we wouldn't see this just be 18 as our answer. They got a different answer. And that answer that they got is, well, let's do it in our calculator. We got 309 times 789. And then divide that by 1496. And you'll notice that our original temperature of 309, because we halved our volume about, we're going to have about half that temperature here. And so temperature 2 is equal to 162, and we can just round it off. Yeah, 163 Kelvin. If we want to know what that is in Celsius, we just subtract, and we get the new temperature in Kelvin. So that's Charles' law. So Boyle's law is, let's get rid of that. Let's go to, so Boyle's law, so far, if we're looking at our little cheat sheet we're filling out, Boyle's law was pressure 1, volume 1 equals pressure 2, volume 2, and the temperature and the amount of gas are constant. In Charles' law, we have volume over temperature equals pressure, or sorry, wow, skipping ahead. Volume over temperature, and in this case, we're keeping pressure and amount constant. So far we've been keeping amount constant, and we've kept temperature constant and pressure constant. So now we're going to keep constant amount again, but in this case, we're going to do the next guy, which kept volume constant. And this, our little simulation does do a good job of demonstrating. So what happens to the temperature of a gas if we, to the pressure of a gas if we heat it up? So as you can see, we're at 300 Kelvin. We're at about, let's see if we can get to 25. There we go. So we're at 300 Kelvin. We're at 25 atmospheres. If we heat this up to 600 Kelvin, should that say 50? Well, let's find out. It's too hot. There we go. As you can see, at 300 Kelvin, 25 atmospheres. At 600 Kelvin, we have 50 atmospheres. So Gay-Lussac Gay-Lussac's law is one where we're comparing the pressure and the temperature, and we found that they are direct. The volume is being held constant, and the temperature is being held constant, or the amount is being held constant. So this law I like to call the don't put unopened cans in the microwave, don't put unopened cans on the stove, because what happens is as you heat something up, it will directly go up together. So the pressure will go up the same amount that the temperature does. So if you just keep heating it up, eventually you're going to cause the pressure to be so high inside that can that it's going to bust open your can. So if we look over here at our book, we have a pressure cooker is a good example of this. Once it has a release valve on it, so once the pressure gets to a certain point, it can release that pressure. If it didn't have that release valve, then we would basically be making a bomb when we made it. So bad news for that. So it's a direct relationship. So just like Charles' law, we're going to use division. And again, we have to use Kelvin, because if we don't use Kelvin, we don't have the correct proportionality. So there's the example, there's the words. We've got direct relationship. The temperature has to be in Kelvin. So if we look at an example here, we have, yeah, I want the red one. Red is fine, thank you. We have pressure over temperature is equal to pressure 2 over temperature 2. So a sample of a gas is closed container at temperature of 100 degrees C. So there's our temperature 1, and a pressure of 3 atmospheres. So there's our pressure 1. They then heat this up to 300 degrees C, and they want to know what's the pressure inside of that chamber. So remember that the first thing we have to do is we have to change these temperatures into Kelvin. So this is going to be 100 degrees C plus 273. So temperature 1 is equal to 373 Kelvin. And temperature 2 is 300 degrees C. And we have to add the 273 to that to give us the 573 Kelvin. So again, this would be a good example if you did this practically in your lab, how Celsius was not the correct temperature scale, because it looks like we've tripled the temperature, but as you can see in Kelvin, we didn't even double it. And so our corresponding pressure change corresponds to the Kelvin change and not the tripling that we saw with the degree C. So again, we're interested in pressure 2, so we're going to solve beforehand. So we're going to multiply both sides by temperature 2. This cancels temperature 2. And so down here we can write pressure 2 is equal to pressure 1, temperature 2, all over temperature 1. Start plugging in our numbers. Pressure 1, 3 atm. Temperature 2, 573 Kelvin. Temperature 1, 373 Kelvin. So notice, again, logic of these problems works really well. They are direct relationship, so they should both go up or they should both go down. Our pressure went up, so our answer should be larger than 3. So let's put it in our calculator and see if we get an answer larger than 3. 3 times 573 divided by 373 gives us 4.6. So our new pressure will be 4.6 atm. And again, Charles's work and Gay-Lussac's work and Boyle, all of them kind of, even though they were separated by quite a bit of time, they all used each other's works. And Gay-Lussac was a great example of how temperature scale needed to change, and Kelvin came in and defined that for him. But as you can see, if Celsius was true, our answer should have gone from 3 atmospheres to 9 because we tripled the temperature. We should have tripled the pressure. But in reality, when we did it, it went from 3 to 4.6. And so we could back engineer that math and find, hey, there's that 273 addition factor that seems to be in there. So that's where that all comes from. So these are the 3 laws. So if we go over to here, we now have pressure 1 over temperature 1 equals pressure 2 over temperature 2. Make sure that you know that temperature is in Kelvin. Oh, sorry, this one doesn't have temperature in it, so erase it, go away. All right, we want temperature is in Kelvin. So what is the combined gas law? Well, in the case of Boyle, we held temperature and amount constant. In the case of Charles, we held pressure and amount constant. And in the case of Gay-Lussac, we've made volume and amount constant. Well, what if we just hold n constant, amount? What if we just hold that constant? And the answer is we can combine all these 3 together. So Boyle's law, all over the Charles law and Gay-Lussac's law added in. So the combined gas law. So we have Boyle's law, and then we add in Charles' law. If we just look at that. Oh wait, let's do this. There we go. And then we have Gay-Lussac's law if we ignore the volume. So this is what's called the combined gas law, where the only thing that's being held constant is amount. Temperature does have to be in Kelvin. So let's take a look at a problem from your homework or your practice problems on page 6, because that's where you can go to do more of these problems. If we look at all of these problems, what we're going to be doing is we're going to be making a list to decide what is the thing that's missing and what is the thing that they are telling, what are the P, the V, the T, or the N, what are the things that they're telling us, and that's what's going to help us do the problem. So let's take a look at number 4, because 4 is an example of the combined gas law. So one of the most important things when doing these problems is making a list of the information that you're given. I'm going to cut to the new snapshot. There we go. What you need, Cherish? You want to unmute yourself? You want to ask in chat? Here we go. Unmute. There you go. You can talk. Oh, I didn't. Oh, there we go. It moved you guys around. Oh, do you not have a thing, Cherish? Can you go to the bathroom? Yes, you can go to the bathroom. Anyway, so let's take a look at problem number 4. If we look at problem number 4, it says, what would the volume be? Let's highlight it. Use yellow highlighter. What would the volume be? Come on, select it. Sorry, my computer's lagging out. What would the volume of a gas at STP, there's STP, if it occupies 255 milliliters at 25 at this? So if we make a list, it wants to know what is the volume if at STP, so standard temperature is 0 degrees C, and standard pressure is 1 atm. What is the new, or what is the original volume if this is what we change our gas to? So notice that if we're looking at our cheat sheet, this uses everything but amount of gas. So we need to use what's called the combined gas law. So P1, V1, T1, P2, V2, T2. We want V1, so we're going to divide both sides by P1. So I'll put that down there. And we're going to multiply both sides by T1. So now we have V1 is P2, V2, T1 divided by T2, P1. So our pressure 2 is 650 mmHg. Our volume 2 is 255 milliliters. Our temperature 1 is standard temperature. Remember that STP, standard temperature and pressure, is 0 degrees C. Now, if we just plug into this problem 0 degrees, well, that's going to ruin the math on this. So we have to add 273 to both of our temperature in 73 Kelvin, and temperature 2 is going to be 25 plus 273 to give us 298 Kelvin. So temperature 1 is 273 Kelvin. Then we're going to divide this by temperature 2, which we just said was 298 Kelvin, and then pressure 1, which is standard temperature, which is 1 atm is what I've written down. But remember that your pressure measurements are all equivalent. So 1 atm is the same thing as 760 mmHg. So rather than converting the mmHg into atmospheres, let's just use 760. So let's use our logic and think about what the answer should be. Remember that pressure volume is indirect, but temperature volume and temperature pressure are direct. So the volume is changing. The volume in the second instance is 255. But the temperature has gone up from 0 to 25, or from 273 to 298. And the pressure was 760, but has now gone down to 650. So we have the temperature going up, which should make the volume go up, but we have the pressure going down, which should also make the volume go up because they're inverse. So we should get a number that is larger than 255. Well, let's see what we get. Now, here's the mistake a lot of students make is algebra in their calculator. This is 650 times 255 times 273. Now, the mistake that people make is they hit divided by, and then they just plug in these numbers. We can't do that. We have to go parentheses 298 times 760 parentheses. Notice that that number is around our answer, 255. It says basically it's 200. Let's see if that makes sense. Should the volume have gone down? Well, or sorry, should the volume have gone up from 200 to 255? So the volume originally started at, according to our answer, 200, and our temperature originally was 0. Our temperature went up, which should make the volume go up. However, our pressure went down by quite a bit. So that should make the volume go up. So let's make sure we wrote everything in the right place. Where did I make a mistake? Because it should be bigger. The logic would say it's bigger. Because the temperature goes up and the volume goes down, which should make the volume go up from the original amount. Either way, answer's 200. That's what my key says, and I just been talking for too long. So that's how we use the gas laws. You want to make a list and plug in your numbers, and then you should come up with the right answer. If things aren't changing too much, then as long as your answer is very close to what you see things changing as, our temperature barely changes at all. It goes up by a very tiny amount. Our pressure goes down, but again, it doesn't go down by very much. So again, we should see, oh, I'm so crazy. The volume does go up because the answer is 255. I'm so sad I didn't see that. 200 to 255. So yes, everything went up like it was supposed to. Duh. My bad. I apologize for that rambling at the end. I'll cut it out of the video. Or I won't. You know what? It's okay. We'll leave it in. I forgot a pencil. Thanks. So that's it. Those are the gas laws. Charles, Gay-Lussac, Boyle, and then the combined gas law. There's good videos to watch for this. If you go to Classroom, if you don't like my rambling and you don't want to sit through an hour and 10 minutes of this, then the helpful videos for chapters 13 and 14, Kinetic Molecular Theory by Professor Dave. We have gas laws over here. And then this one's covering kind of what we're doing next time. This thing kind of covers everything we talked about. So you can watch either of these videos. He does get into the ideal gas law, which is what we'll talk about next week. So hope this helped. I'll put the VOD up in a few minutes after it is done rendering. Are there any questions about the gas laws? Do you guys want to have 2 live sessions where it's like I talk, we go over it, you try it, and then I can pop up a live session that's just question and answer? You can send me an email if you think that's a good idea. But anyway, that's the end of the meeting if none of you have questions. Okay, I'm going to stop recording there.